but because some people in the morning weren't able to get that done, we had something else. Normally when I do covalent bonding, I talk about hydrocarbons with you guys, but we're not going to, we're kind of behind schedule to say the least. So I'm going to skip that part. That's like a little extra that's not normally even part of the regular high school curriculum. But those of you that are going to be doing medical things or engineering things are probably going to have to take basic chemistry and organic chemistry, which is the chemistry of carbon. So that's, I thought I'd just give you a little quick taste of it with that ed puzzle. But there was a typo. One of the last question, the correct answer, somehow I put a line space, and so you couldn't see the answer. Anyway, don't worry about it. Your score isn't what I record. I just record that you did it on Wednesdays for your attendance. So I think everybody just about in here did it, so we're good. All right, so, but I do want to talk about carbon chemistry. So we need to talk about that briefly, just to make sure some of it sticks in your brain a little bit. Simplest hydrocarbon. First of all, what is the hydrocarbon? Hydrocarbon, what is it? Hydrogen and carbon only. Okay. So that's a start. And the simplest one, that has some weird names. So they start naming them with prefixes based on the number of carbons. Don't do drugs, kids. So you remember that, right? So meth is the prefix for one carbon. F is prefix for two. Prop is the prefix for three. And bute is for four. Now, why didn't they just do them like normal geometric things? I don't know. I didn't make it up. It's not my fault. Okay, but if you have 5 carbons, it starts going normal geometry. So pent, 6 is hex, 7 we use hept, 8, of course, like an octopus is oct, 9 is non, and 10 is dec, like a decade. So they start getting normal, and these first 4 are weird. So meth, F, meth, and then the other piece to naming them has to do with the suffixes, depending on the types of bonds. So if all there are single bonds, what's the ending? Do you remember? A. So what is A and E? Oh, yeah. And then if there's a double bond, this has to be one. There could be lots of single bonds too, but if there's a double bond in it, it's ene. And if there's a triple bond in it somewhere, it's ine. So this one's kind of cool because A, B, Y, right? Like our vowels are in alphabetical order, so that if you do things like that to help you remember stuff, that's an easy one. I can't help you. Monkeys eat peeled bananas is a stupid way to remember meth, F, prop, bute. Why would you come up with that? I have no idea, but somebody did. Monkeys eat peeled bananas. Most people do. most people. Anyway, I guess you could eat the bananas to get that. Anyhow, so meth, F, and prop are all gases at room temperature. They're small hydrocarbons. Butane is the hydrocarbon that's in lighters. Okay, so once you get into these, they're liquids. Octane. Anybody know where you can find octane? In your car, okay? So the fuel that we use, the hydrocarbon that we use to fuel our vehicles, most of us, is a hydrocarbon, primarily octane, but there's other stuff in there. It's not just straight octane. And so when you go to the gas pump and you see 89 or 91 or 93, it's talking about the percentage energy content relative to a full, 100% octane. So it's a liquid at room temperature. There's other things that they mix in. So 89, if you buy the low end gasoline, that means it has the energy content of a liquid that has 89% octane in it. That's the easiest way to explain it. Let's try this one more time. Of course. So this is 2 carbons, single bonded. This is ethane. This is 2 carbons, double bonded. So we call it ethene. Okay. And this is 2 carbons, triple bonded, ethine. Ethine. We actually call this acetylene, but at any rate, that's not the correct name. This is the correct name. What do you notice happens? Same number of carbons, different number of bonds, different number of hydrogens. So there's actually a little formula to calculate how many hydrogens need to go with how many carbons, and they get progressively less. The anes have the most hydrogens, the enes have fewer, the ynes have the least. Okay. So quick and dirty. And then of course you can substitute things on. So like I could take this, well now it's 6 carbons, so what is this? X, yeah, so I can substitute in a, gotta make sure I get all my hydrogens here, sorry. I can take a methyl group and methylate this hexane, and then I just have to say what carbon it's on. So this is on the 3rd carbon, there's a methyl group, so we'd say 3-methyl hexane if it's all single bonds. And it gets crazy. Hydrocarbons branch and branch and branch and branch, and it's nutty. But once you understand the code on how to name them, it's really not too terrible. All right, any questions on hydrocarbons? The fuel of... How come I say propane's a gas? Anybody have a barbecue grill? Is it gas in that tank? It's liquid. How come? How about your little green canisters for your camping stove? It's gas at room temperature and normal atmospheric pressure. So they compress it into a liquid to make it easier to transport, whether it's a big propane tank that heats your house, or it's the little propane tank at your barbecue grill, or the little tiny one at your camping stove. It's still propane, but it's under pressure. And so when it comes out to normal atmospheric pressure, then it turns into a gas again. All right. I think that's everything for that for now. Any questions? Okay, so the next item I want to show you is I posted a hopefully legible table of electronegativities for you in the classwork feed. You want to pull up a tab of that for me, please, so you have it, because I'm going to ask you about electronegativities. Like, go into the classwork and then just pull it aside so you can use it. And the notes are here, and we're not going to get all the way through these today either, but we'll get started on them. Okay, let's get rolling. So we were talking about what kind of, that's my electronegativities, where is it? There it is. We were talking about bond character, what type of bond exists between the atoms, and go. So there's different electronegativity values for each element, and one side might be pulling harder on the electron pair than the other side. In addition to what's inside the molecule, there's also forces that act between molecules to determine whether it's going to be a liquid, solid, or a gas at room temperature and normal pressure. And those are called intermolecular forces, and we're going to get into those tomorrow. Those intermolecular forces are determined by 2 things. It's not just the electronegativity difference between the elements. It's also, so remember, inside the molecule, right? So carbon and oxygen, and most of you made this molecule, I think. That is going to be either non-polar if it's a small difference, polar if it's larger, or ionic if it's 2 or greater. However, just because there's polar bonds inside doesn't make the molecule polar. We have to look at the geometry. So again, group 1 and group 2, one thing attached to it, 2 things attached to it. The only chance they have is a linear shape. Once you get to group 3, boron's family, 3 things can bond, and that's trigonal when there's 3 things bonded. And those are all flat. So we call it trigonal planar. Carbon's family ends up with the, oh, I lost my, heavens to purgatory. There we go. Carbon, what shape is a methane molecule? It's back rubber shape. What shape? There's 4. There's 4. Tetrahedral. Okay. So that shape. And then if you're in group 5, like nitrogen, you've got 5 valence electrons. Most of the time, 3 things bond, and you have your little lone pair, bunny ears. Oxygen, 6 valence electrons, usually only 2 things bond, okay, and 2 lone pairs. Okay? So knowing where it is helps you with your geometry. But again, just because you know let's go back to electronegativity. Just because you know electronegativities of things doesn't, if there's a big difference, doesn't make the molecule polar. So this is carbon dioxide. What's the electronegativity of carbon? Anybody? Carbon's electronegativity, look on your thing. 2.5. What's the electronegativity of oxygen? 3.5. What's the difference between them? 1.0. So what character does this molecule, this internal bond have? What will we classify this bond? Other than a double bond. But what's the bond character? Is it ionic? Is it polar covalent? Or is it non-polar? Polar covalent. So if you have an electronegativity difference of 1.0, that's kind of funny, delta, delta. This is polar covalent bond. We usually just say polar, however. Guess what? This oxygen also has an electronegativity of 3.5. This also is a polar covalent double bond. Okay? So if you're pulling equally hard on each side, this molecule is non-polar. So even though the bonds inside of it are polar covalent, we usually leave the covalent off, which is really annoying because it gets confusing. But this molecule is non-polar. That's why CO2 is a gas. It doesn't like to stick to itself. There's no lone pairs. Well, there's lone pairs on the oxygens, but they're repelling each other. Okay, there's nothing for them to stick to. So CO2, carbon dioxide, non-polar molecule, even though it's got polar covalent intramolecular bonds. That's a lot of words. Okay. All right. Again, though, nitrogen, these are all hydrogens in ammonia. They all have the same bond character. What's the electronegativity for hydrogen? Good job. And for nitrogen? So the difference between these is 0.9. This is also a polar covalent. Okay, but this isn't flat. This has the lone pair, so those hydrogens are pushed out of the plane. So this is going to make a polar molecule, as is the water molecule. So water molecules, 2.1 for hydrogen, 3.5 for oxygen. Big. Oh. 1.4 difference. Okay, very much a polar covalent bond. However, the bigger part of it is that these hydrogens aren't side by side, right? They are 2 lone pairs. So that makes this a very negative side and this is a positive side. The positive of one molecule is going to be attracted to the negative of another. When water is a liquid, it just kind of slides around each other and falls apart. However, what does ice do in liquid water? It melts. It floats. Yeah, any other solid isn't going to float in its liquid. It's going to sink, solid sink usually. But because water has to be oriented just a certain way, the volume ice, the solid, takes up is much greater, not tons greater, but about a percentage greater than the liquid. And so the solid will float. It's crazy. It doesn't make any sense. It will melt too, yes. All right, so polar covalent bond inside and very polar molecule because of the lone pairs. All right, let's do a little practice. The first one is hydrogen with chlorine, hydrochloric acid. Is there symmetry? That's another way you can tell about polarity too. Is there symmetry? Are there equal things on both sides? 3.5, isn't it? Oh wait, what's chlorine? Is it 3.0? Chlorine's 3.0, huh? And oxygen's 3.5. So chlorine's 3.0, hydrogen's 2.1, 0.9 difference. Chlorine's winning the tug of war. It's very much polarized. Negative on the chlorine side, positive on the hydrogen side. Ammonia, we just went over. It's a polar molecule because of the lone pairs. It's not symmetrical in 3 dimensions. Boron, what's the polarity or electronegativity of boron? 2.0. And fluorine, which we all know is the highest, is 4.0. Big difference. This is ionic. However, 3 things around the central atom, all in a flat plane, trigonal, planar. This one is non-polar, okay? That molecule doesn't want to stick to itself, if you will. If there's equal things all the way around on a carbon, like carbon tetrachloride, which is shown here, that tetrahedral shape, equal poles in all directions, 109.5 degrees, that is going to be non-polar. Even though the internal bonds between carbon and chlorine are polar, the molecule is symmetrical all the way around in all dimensions. It's not going to stick to itself. This one, on the other hand, though, if I took a methane and plopped on, I did a halogenation, right? I plopped on a chlorine. These are all equal, but this one's not. So it's going to be electronegative. The electrons are going to get pulled towards the chlorine like the arrow is showing. Okay. All right, another crazy thing about polar molecules is they orient themselves in an electric field. Okay, so one end of the molecule, remember dipoles, 2 poles. One end's positive-ish and one end's negative-ish, even though they're neutral. That dipole then is going to attract the positive side of one to the negative side of another. And so in a liquid, it's going to be kind of jumbled. In solid water, ice, it's going to have to orient a certain way to freeze. But we can also do that artificially by applying an electric current against putting the substance between 2 electrically charged plates, and the molecules will orient themselves. And so if this is hydrogen chloride, hydrogen's positive, chlorine's negative. In a liquid, in a normal situation, they're just kind of all over. However, they're going to orient the positive side of the molecule to a negative electric current. The negative side of the molecule will be attracted to the positive electric plate, and it will line up. And what's super cool about this is that concept actually, I totally went on a bird walk this morning, so I'm going to share it with you. That concept actually is how we figured out about plate tectonics. So what's plate tectonics? You guys know? The crust of the Earth, right? Remember, if you think of the Earth like a hard-boiled egg, kind of similar, right? The egg shell is like a crust. That's where nobody will ever go anywhere other than the crust. Okay. Sometimes magma gets pushed up to the crust because of some faulting and stuff, but you're not going to go far enough down into the crust to get to the magma. Okay, ever. No one is. The plates move. So here's the really crazy. Have you guys seen the volcano in Iceland? That's amazing. So nobody all day today has seen it. I'm just so bummed. I'm so glad you're here because I'm going to tell you about it. Currently, there is a volcano erupting on the island of Iceland. And you can watch a live, oops, I didn't want to go that far, a live feed of it. They had like 54,000 earthquakes last month. You're a small business. Mm-hmm. That's a lot of earthquakes. Yes. Yes. So if you have a volcano going to erupt, that's one of the signs. And so there's actually a live stream you can watch the volcano. How far away? It's Iceland. Ooh, great question. Of course, that would be an excellent question to know the answer to. I don't. But it's down here. If you've been, my plan is to go to Iceland because I want to go see the Northern Lights sometime on my bucket list. And so the capital of Iceland is Reykjavik, whatever, right here. It says a mile. 1 kilometer. That's not a mile. So about half a mile. The volcano started erupting on Friday, I guess. Yeah, I thought it was over the weekend, but something I saw said Friday. And this is one that's not shooting lots of ash into the air. It's just kind of oozing out. And the reason for that is because Iceland has the Mid-Atlantic Ridge runs right through the island. So what's the Mid-Atlantic Ridge? It's a giant mountain range in the middle of the Atlantic. Okay. Probably most of you have seen a globe or a map before, and you could look at South America and Africa and go, they look like puzzle pieces that would fit together. Yes? People noticed that before. Okay. We also know that there's tropical fossils, big, huge tropical plant fossils down in Antarctica. And there's rocks in the Appalachians that are the same as rocks in Scotland. And we have all this evidence and all these pieces of information that say this landmass should have been stuck together somehow, but they couldn't figure out the mechanism until after World War II. So in World War II, developed sonar, and we were doing a lot of ocean floor exploration, found this giant mountain range on the bottom of the Atlantic. Turns out that mountain range goes right through Iceland, comes to the surface at that point. But down here, it just is there. And so, that was awful. The cool thing, and this is why I went off on this bird walk, is they figured out, finally, after taking some samples and checking, again, the Earth's like a giant magnet, right? It's actually, I think it's negative relatively to a magnet and positive pole at the South Pole. But through the Atlantic is this crack in the ocean floor. And on either side of it, as this stuff is oozing out, the magma is oozing out, of course, once it hits the ocean water, it cools and solidifies. And what ends up happening, you always see it drawn kind of like this, is all along that crack, the crystals, the iron crystals, are oriented a certain way. Okay, it turns out, because it kind of oozes up and it kind of floats off, right? The bands of these crystals, the orientation of the crystals is exactly the same width, exactly the same distance from the Mid-Atlantic Ridge. And then there's other crystals, different size band, but the same on both sides. I don't know if you know, but our polarity is changing. Okay, so it used to be about every, I think it was 100,000 years or so, they estimated that the Earth's poles flipped. We think we're in a start of a flipping process. We're quite a few 100,000 years later than normal, but on either side of the ridge, the polarity keeps alternating back and forth. So when it's like the orange one, it's negative on top and positive on the bottom, if you will. And if it's like the blue, it's positive on top and negative on the bottom. So you know how compasses, magnets work and pulls the compass needle around? The little grains of the iron crystals have also flipped. Yeah. So I could, let's see. I used to know numbers better when I was teaching earth science, but polarity of Earth magnetic field, there it is. Earth's magnetic field alternated normal polarity. That's what we're living in. We call it normal because that's what we have. And polarity on its opposite. These are called primes. Reversal occurrences are statistically random. So there's not like a set amount of time. There's been 183 reversals over the last 83 million years, about once every 400,000 years, 450,000 years. I think we're around 700,000 since the last one. A long time, longer than. But our compasses are going to be backwards, so they're going to be oriented wrong, and so it actually has some problems for navigation, and the geomagnetic pole actually does shift. It's shifting. So if you do anything like orienteering, anybody know about orienteering? The Swiss Army used to do this like a competition where you go out, you got a compass, you got a little map, and you got to know how many steps your pace is, and you have to go trekking through to the backwoods. Anyhow, but yeah, you have to adjust because geographic North Pole isn't geomagnetic North Pole, and you have to do all sorts. Anyhow, it's just crazy. So these little stripes like this, we see that alternating pattern of the crystals. And so here's a really crazy thing. Look at this. So the reason why I went off on this is because the volcano is so cool. And let's find Bjorn's drone. Well, there's thankfully not people right there. So that's 3 days ago. But actually, here, I'll show you something. There are people. There's not a city right close, but you can see there's people trekking to it. There's a lot of people going to see it. Helicopter. So there's a guy that flew like a 2,000, not pounds. Pounds and dollars aren't equal, but an expensive drone over the top of it. And then there's people hiking all around. So the perspective's kind of hard to get because it looks like you're a lot closer than you are on some of these angles. But they showed some people like frying bacon and eggs on the lava, and it ended up blooping over and melting the pan. Yep. Magma's under, yeah. So yeah, so the magma is heated from compression, and it's also from nuclear decay inside the core, is what we think. And so yeah, it just oozes up. So this is basaltic, which is typical of oceanic crust. But anyhow, it's really very cool. And there's probably going to be somebody stupid try and take a selfie and get hurt. But anyway, sorry. What's that? No, that's just zoomed in. But there's some people that have.
So our expectations are that with this topographically confined area, if we get this
look at all those people.
And it depends on how long the eruption is on. But there's just one spillway, and that's over there. So if the eruption continues for a longer period of time, we have a point of show that backup.
Yeah. Yes. And so the other thing, you're right, absolutely, they can feel it. You notice there's no snow there, but there's lots of toxic gases that come off of volcanoes too. So that could, if it burps a big load, it could kill some people from that too. So I don't know. I don't think I need to be right that close, but I do want to see a volcano and the Northern Lights. So anyhow, all right, total digression, but it's still cool and it's still science. So I thought so too. All right, you have to finish up your lab. How many of you still have to go build? Anybody? This class is all the way done? Part 2 and 3, so once you do the double and triple bond stuff, you're good? All right, so I just want to remind you before I let you loose that there are pre-lab questions that you need to do. Make sure you answer those on the document. If you make drawings, do them on the papers that I gave you. And then for the post-lab questions, you can just answer them here on this, okay? And if you're welcome to work at the lab stations with your partner. But that is all I have. And then those of you at home, you have the simulation to finish up if you haven't finished it. If you have any questions, I am available to answer questions.